Hello everyone, welcome back to the Concepts of Engineering Mathematics course. In the previous lecture, we had seen the application of Cramer's rule to solve numerical problems like simultaneous equations, and we did solve an example. And after that, we started the discussion about matrices. Okay, so in that, we saw how matrices are written and what are various forms or types of matrices. And after that, we had seen the methods of addition and subtraction of matrices. And towards the end, we saw the scalar multiplication of matrix. Okay. So today we will see the matrix multiplication, means multiplication of a matrix with another matrix. But before that, uh, let us see an important point related to the scalar multiplication. Okay, so in scalar multiplication, we always need to note that the multiplication of any scalar with the determinant of A is not same as that its multiplication with the matrix. Okay. So means that if we multiply K with K to determinant of A, then this is not same as that of determinant of K multiplied to A. And this is due to the fact that when we multiply any scalar to a determinant, it gets multiplied to any one of the rows or columns. Okay. But when we multiply the scalar with a matrix, then it gets multiplied to each and every element of the matrix. Okay. So what should be the relation? If this is not valid, then the determinant of K multiplied to A will be equal to K to power n, and this is valid for square matrices only because determinant can be found for them only. Okay, so K raised to power n multiplied with A. Okay. Why is it so? Because uh, here what happens is, this is determinant of A. Okay, so here what happens is K is taken common from each of the row or each of the column. So suppose there is a nth order matrix. So from the first row, second row, third row, so on up till nth row, we take K out. So K gets multiplied with K till n powers. Okay, so this will be K to power n multiplied with determinant of A. Okay. So this is the valid relation where n is the order of A. Okay, so we need to keep this in mind during the scalar multiplication. Is order of A. Okay. So now let us see the matrix multiplication. Okay. That is the multiplication of a matrix with other matrix. So we will now discuss the matrix multiplication. Okay. So suppose we have a matrix A and other matrix B, and we need to multiply them. So let me drag it like this. So we have say A is suppose A, B, C, D like this. And then we have other matrix B, which is say E, F, G, H. Okay. So we now need to find C, which will be multiplication of A with B. Okay. So the formula for this is simply row into column. We need to follow this basic formula, which is row into column. So how is this implemented? Let us see. Row into column like this. Okay. So this is done in the way like if we want to find C11, then we will have to multiply this first element of the first row of matrix A with the first element of first row of the matrix B, and then it is added with the product of second element of first row of matrix A with the second element of first column of matrix B. That in this manner, the row into column multiplication is carried out. Okay, so what I want to say is we write this as say A11 is multiplied with B11 and it is added to A12 multiplied with B21 and so on. Okay. So this is the way to do this. So here we will get AE plus BG. Similarly, we can find C12. Again, here what will happen is we will multiply this first row of A with second column of B. So how is it done? So here we will have A11 multiplied with B12 and it will be added to A12 multiplied with B22. Okay. So this will result in this will be AF plus BH. Okay. And this pattern is followed. Okay. So basically we can write that Cij is nothing but this can be written as say AI1 multiplied with B1j, which is then added to say AI2, and this is now written as B2j. Okay. And this goes on. Okay. Like this. So so on up till say AIN into B and J. So this is the general formulation. Okay, so here how this is written after multiplication. So this entire C matrix can be written here as first two we have determined as AE plus VG, okay, and this was AF plus BH. Similarly, we can write this C21 as second row of A multiplied with first column of B. So this will be CE plus BG, and this will C22 will be second row of A multiplied with second column of B. So this will be CF plus BH. So in this way, this is done. Okay, and this formula can be written in a short form as Cij is nothing but the summation of Aik multiplied with Bkj, where k is value. Okay, k varies from 1 to n, where n is the order of these matrices. Okay. So in this way, the matrix multiplication is done. Let us not write this as 1 to n because multiplication is not necessarily done for square matrices. Okay. So this is the general way of multiplying. Also, one more important thing to note here is that the product of two matrices A and B is possible only if their internal dimensions match. which means that the number of columns of A should be equal to the number of rows of the matrix B. Okay, only then their multiplication will be possible. Okay, so multiplication is possible only when multiplication is possible only when number of columns of A, number of columns of A, what is happening here? So number of columns of A are not are, it is only when number of columns of A is equal to the number of rows of B. So this is the necessary condition for the feasibility of matrix multiplication. So we will solve an example to have a better understanding of this matrix multiplication. Basically, what does this statement means is that suppose we have a 3 cross 3 matrix which is being multiplied with a 3 cross 2 matrix. Okay, so this multiplication is feasible. Okay, and this will result in the matrix with dimensions having these two. Okay, so this will result in a 3 by 2 matrix. Okay. Similarly, if there is a matrix with dimensions say 3 by 1, say 3 by 1, and it is being multiplied with a 1 by 3 matrix. So again, this is feasible and will result in the dimensions having 3 by 3. Okay, so 3 by 3 matrix will be formed here. Okay, so this is also feasible. But suppose if we have a matrix of the order 3 by 2 and it is again being multiplied with a matrix with order 3 by 2, so this will not be feasible. Okay. So this is not possible. Okay. So the meaning of this statement is like this. Okay. So before we solve the example, let us see some of the properties of matrix multiplication. Okay. So now let us see the properties of matrix multiplication. So, like there were certain rules or properties for addition and subtraction. There are some for multiplication also. Okay, so what are those? So very first property is that matrix multiplication is not commutative always. It may happen sometimes that product AB is equal to product BA, but generally the matrix multiplication is not commutative. So multiplication of matrices is not necessarily commutative. Is not necessarily, or let us write that it is not generally commutative. Is not usually commutative. And what does this mean? It means that the product AB that is AB will not be equal to BA. Okay. So this is the very first property. The next one is that the matrix multiplication is associative, but only when the conformability is assured, which means that the order of multiplications should be maintained, and also the point that internal dimensions should be matching. This criteria should also be met. Then only the matrix multiplication is associative. Okay, so matrix multiplication is associative if conformability is assured. If conformability means feasibility in a sense. So conformability is assured. And what does this associativity means? It means that A multiplied with the product of BC will be same as the product of AB being multiplied with C. Okay, so this is the associative law. Also, the next property says that matrix multiplication is distributive with respect to addition. Okay, it can be with respect to subtraction also. So matrix multiplication is distributive. Matrix multiplication is distributive with respect to addition and subtraction. Okay. So with respect to addition and subtraction. So what does this mean? It means that the multiplication can be distributed like this. Okay, so this will be same as the products of sum of products of AB and AC. Okay. So keep in mind here the order matters. Means we cannot write AB plus CA or BA plus CA. Since A is pre-multiplied, so it will be pre-multiplied even after distribution also. So this will be AB plus AC. Okay. The next property is if matrix A is multiplied with identity matrix or unit matrix, it will the value will not change, okay, and the matrix will remain same. Okay, so the next property says that multiplication of a matrix A multiplication of a matrix A by unit matrices results in the matrix A itself. Results in matrix A itself. So what does this mean? It means that since the unit matrix is an identity matrix, so we should keep in mind that the dimensions match again. It means the condition for multiplication should be matched, and generally we consider this multiplication for square matrices. Okay, so suppose that is for say a square matrix, A, we have AI will be same as IA, and then this will be same as A. Okay, so there will be no change here. Okay. Now the next property tells us about the inverse of a matrix. We will see how can we calculate the inverse. Okay. So before that, we need to know that the inverse will exist only if the determinant of A is not zero, where A is a square matrix and non-singular square matrix because the determinant is not zero. So multiplicative inverse. We are writing about inverse in multiplication because we are considering it to be multiplicative inverse. Okay, so multiplicative inverse of a matrix of a square matrix. The square matrix A exists if determinant of A is not equal to 0. We will see why it is so. So for now, this is the property. Okay. Or that is A is non-singular. Not singular. And thus, the relation which comes out is the multiplication of matrix with its inverse, that is multiplicative inverse, or the multiplication of inverse of a matrix with its original matrix is the identity matrix, means the result is identity matrix. Okay. So this is one of the properties. Now next property is also very interesting, that if A is a square matrix, then the product simply results, means let us write that down, that if A is a square matrix, then what happens is the product of A into A is simply A square. Okay. And similarly, the product of A into A is simply A cube, and so on. Okay. The next property is that any matrix raised to power 0 is simply the identity matrix, where A is some square matrix. Okay. And also the property which is very interesting is that if we raise the identity matrix to any power, it will again become the identity matrix of same order. Okay. So where n is any positive integer. Okay. N is positive integer. Positive integer. So these were some of the important properties related to multiplication of matrices. Okay. So now let us see the multiplication of matrices with the help of examples. Okay. So let us see the question where we are given with two matrices A and B, and we know we need to find the products AB and BA, and also from that product we can check whether the commutative law is valid or not, means AB is equal to BA or not. Okay. So our first property of matrix multiplication will be validated there. Okay. So suppose if we are given with matrix A as 1 1, 2, -3, and the next column is -2, 3, and 1. And next we have 3, 1, 3, -1, and 2. Okay. And the next matrix given to us is B, which is 1, 0, 2, then 0, 1, 2, and then 1, 2, 0. Okay. So now we need to find C equal to AB and say D equal to BA. Okay. So we now need to find both the products. Okay. So let us see the solution. So how can we proceed? Simply C will be A multiplied by B. So we have C as, let me write with some space so it is clearly visible. Okay. So we have A as 1, 2, -3. This is -2, 3, 1, and this is 3, -1, 2. This is being multiplied with B, which is 1, 0, 1. This is 0, 1, 2. This is 2, 2, 0. Okay. So we will now simply follow the rule for multiplication, that is row into column. Okay. So here the C matrix can be written as first row of A multiplied by first column of B. So this will be 1 into 1, 1, plus -2 into 0, that is 0, and 3 into 1 is 3. So this is the first element of first row, first column. Yes. Now next one is the element at position of first row and second column. So this will be again row multiplied by column. Means the first row of A multiplied by second column of B. So this will be 1 into 0 is 0, plus -2 into 1 is -2, and then 3 into 2 is 6. Okay, similarly here we have 1 into 2 means the first row of A multiplied by third column of B. So this is 1 into 2 is 2, then -2 into 2 is -4, and then 3 into 0 is 0. Okay. Similarly, in the second row, we will have the second row of A multiplied by first column of B first. So this will be 2 into 1 is 2, then 3 into 0 is 0, then -1 into 1 is -1. And now we will have to multiply the second row of A with second column of B. So this will be 2 into 0 is 0, then 3 into 1 is 3, and then we have -1 into 2 is -2. Okay. Then we have the multiplication of second row of A with third column of B. So this will be 2 into 2 is 4, then 3 into 2 is 6, then -1 into 0 is 0. Okay. And similarly here, third row of A multiplied by first column of B. So -3 plus 0 plus 2, and then 0 plus 1. Here we are multiplying the third row of A with second column of B. Okay. So this is 1 into 1 is 1, then 2 into 2 is 4. And now we have third row of A and third column of B. So this will be -6, and then plus 2, then 0. Okay. So in this way we can solve these values and we'll get the product AB. So this is 4, again this is 4, and this is -2, and this is 1, this is again 1, this is 10. Here we have -1, this is 5, and this is -4. So this is the product of A and B. Now let us find the product BA. Okay. So now similarly we can find BA, and see here both A and B were 3 by 3 matrices. Okay. So this is also 3 by 3 and this is also 3 by 3. That's why the product was possible here, because the internal dimensions were matching. Means if this is 3 by 3 and if this is also 3 by 3, so these dimensions were matching, and the finite dimensions that we got came out from these values. Okay, so these are the finite dimensions, 3 by 3, 3 by 3 we got here. So we need to keep in mind the dimensions also. So now let us find the product D, which is B into A. And let us see if this is possible or not. Then if we are trying to find B into A, then in that case, we'll have to see that the second dimension of B is matching with the first dimension of A or not. Okay, so clearly it is matching. So we can now proceed to solve. So let us now solve this for D. So this matrix B was given to us as this was 1 0 1 0 1 2 and then 2 2 0, and this was being multiplied with A, which was 1 2 minus 3, then minus 2 3 1, and this is 3 minus 1 2. So let us find the product again. Okay. So now this time I'll be doing it very quickly. So as we have seen the methodology, so simply first row into first column. So this is 1 plus 0 minus 6, and then we have here minus 2 plus 0 plus 2, and then we have 3 plus 0 plus 4. Here we have 0 plus 2 minus 6. Then we have 0 plus 3 plus 2, and then we have 0 minus 1 plus 4. Here we have 1 plus 4 plus 0. Then we have minus 2 plus 6 plus 0, and then we have 3 minus 2 plus 0. Okay. Again, I have done the same thing, that I have multiplied the row with the column. Okay. So now this results in the product BA, and that is nothing but this is minus 5, this is 0, and this is 7. This now becomes minus 4, this is 5, and this is 3. Now here we have 5, then 4, and then 1. So again, this is a 3 by 3 matrix, because the dimensions, if we see from there, we can conclude that this will be a 3 by 3 matrix. Now if we compare the matrix C and D, so from these we can clearly say that these two are not equal, because for two matrices to be equal, their corresponding elements need to be equal. Okay, means exactly all the elements corresponding in both the matrices will be equal, which is not the case here. So thus what we can say is C is not equal to D, that is AB is not equal to BA. Okay. So this justifies our first property also, that the matrix multiplication is not commutative. In some cases it may be commutative, like we saw for A inverse A is same as A inverse, sorry, A inverse. Okay, so that is a different case, but generally this product is not commutative. Okay, so with this, we will now move towards the finding the inverse of a matrix. Okay, so before that, we will see the concept of adjoint of a matrix. Okay, so basically, adjoint is something which automatically gets incorporated during finding the inverse of a matrix. So let us see what is adjoint of a matrix. So suppose we have a matrix A, square matrix. It should be firstly the square matrix. Then only we can find the adjoint and we can invert the matrix. Okay. So if we have a square matrix A, which has elements like A1, A2, A3, B1, B2, B3, C1, C2, and C3. So here, if we find the cofactors for each element and then using that those cofactors we form a matrix again. Okay. So suppose we have a matrix of cofactor. Okay. So let me write it also. If we find the cofactors for each element, okay, each element, say A1, A2, A3, B1, and so on. B1, B2, B3, and C1, C2, C3. Okay. Let me write them all so it will be very clear. B2, B3, sorry, B3, C1, C2, and C3. So these are the corresponding cofactors of these elements. Okay. Then then form a matrix by these cofactors. So this will be, say, the cofactor matrix. So this will be, say, A1, A2, A3, B1, B2, and B3, C1, C2, and C3. So these were cofactors corresponding to the elements of A. Okay. So this is known as the cofactor matrix. Now, if we take the transpose of this matrix, then the matrix which will be obtained will be known as the adjoint of A. Now, the transpose of the cofactor matrix is known as adjoint of A. Okay. And it is represented as adjoint of A, means A dj of A. So this is written as adjoint of A, and this is nothing but the transpose of the cofactor matrix. And if we write this, this will become like this: A1, A2, A3. This is B1, B2, B3. We have seen that what is meant by transpose. So I'm writing it directly. So C1, C2, and C3. Okay. So this is known as the adjoint of the matrix. Okay. So now we are familiar with adjoint, so we can proceed towards finding the inverse of a matrix. So let us see how to find the inverse. So we will now see the inverse of a matrix. And if we are able to find the inverse, then we will also be able to solve a system of simultaneous equations using this matrix method. So we will now uh, see the inverse of matrix. So again, for matrix to be invertible, it should be a square matrix, because inverse is defined as nothing but the adjoint of the matrix divided by its determinant, and determinant can only be found for square matrices. Okay. So suppose there is a matrix A and another matrix B, and their product equals to identity matrix. Okay. Also here this product will be BA also. Okay, let us leave that part. So here what will happen is, suppose we pre-multiply the inverse of A on both the sides, then this is A inverse AP will be A inverse I, and we have seen that anything multiplied with I remains same. So here this becomes IB is nothing but A inverse. So ultimately B is nothing but A inverse. Okay. So in this way, if any matrix is multiplied with its inverse, it results in the identity matrix. Okay. So A is getting inverted here. Okay, so now let us see how to find the inverse of a matrix. Okay. So how to find inverse matrix. Inverse matrix. So again, we need to follow a certain procedure. So firstly, simply find the cofactor matrix. Find the how to find inverse of inverse matrix of say of A. Okay. Find the cofactor matrix of A. Cofactor matrix of A. Let us call this as AC. Okay. And after that, find the transpose of that cofactor matrix AC. Okay, so take transpose of the cofactor matrix. Cofactor matrix. So this will be, say, that is, we are now finding AC transpose. Okay. And finally, divide the transpose. See, this AC transpose will be nothing but the adjoint of A. Okay, so let me erase this part and write it as, that is AC transpose, or we are finding the adjoint of A. After this, divide this transposed cofactor matrix by the determinant of A. So finally divide by determinant of A. Okay. So what is it means? That is, we have to here we have to divide the transpose by determinant of A, or we can write it as adjoint of A divided by the determinant of A. So this gives us the inverse of A. Okay. Or in simple manner, we can write it as thus A inverse is nothing but AC transpose over determinant of A, or adjoint of A divided by the determinant of A. So using this, we can find the inverse of a matrix. Okay, so we will work out an example, but let us see the method to solve simultaneous equations also, so that both the things will be covered in a single problem. Okay, so simultaneous equations as well as this inverse finding. Okay, finding the inverse. Okay, so let us see the solution of simultaneous equations. Simultaneous equations using matrices. So say this. Okay. So suppose we have say set of equations like again say take a1x plus b1y plus c1z is k1, then a2x plus b2y plus c2z is k2, and then a3x plus b3y plus c3z is say k3. So we have these three equations. We are frequently taking a system of equations in three variables because this is the most generally seen case. Okay, so mostly we face these type of problems only with the system of equation in three variables. Okay, so here we can form three different matrices. Okay, so first we can see is the matrix formed by coefficients. So this will be a1, a2, a3. This is b1, b2, b3, and say c1, c2, and c3. So this is the matrix formed by coefficients. Similarly, we can form a matrix say x, matrix x by the variables. Okay. So these are x, y, and z here. Also, we can form another matrix K with these constant terms on the right hand side. Okay, so this is K1, K2, and K3. So if you'll observe these systems, means these equations can be simply written using the matrix method in a single line. These equations are nothing but the product of m with x, which will be equal to k. Okay. So the entire equation system means equation 1, 2, and 3 are now written as mx equal to k. And now in this relation, if we pre-multiply with m inverse, then let us see what happens. I'm using the term pre-multiplication because I'm multiplying in the very starting of both left hand side and right hand side. Similarly, if we multiply towards the end, then we use the term post multiplication. Okay. So currently I am pre-multiplying with m inverse. Okay, so this is m inverse k, and this becomes I into x, which will be nothing but x is equal to m inverse k. Okay. And from here we can simply find the corresponding unknown variables. Okay, so what we need to do is simply invert the coefficient matrix and multiply it with the matrix of constant terms. Then it will result into the matrix which will be corresponding to the value of unknowns. Okay. So this is the method of finding the solution of simultaneous equation in three variables. So before proceeding to the solution of equations, we need to understand the concept of rank of a matrix. Okay, so now let us see what is meant by rank of a matrix. Okay. So we'll now discuss the rank of a matrix. This will determine the consistency of equations. Okay. So rank of a matrix. So the rank of matrix A is said to be R if the rank of matrix A is said to be R if it has at least one non-zero minor of order R. Okay, means R is the order of highest order non-zero minor. It seems that this statement is very complex. So let us write it down that it has at least one non-zero. Okay, so and matrix A may have several minors of various orders. Say the matrix is of the order of 5 into 4, means there are 5 rows and 4 columns. Then there will be several minors, say of the order of 4 by 4, or say 3 by 4, 1 by 4, 1 by 1, 2 by 2, 3 by 2, and so on. So there will be several minors. Okay, so there should be actually minors will be in the form of square matrices only, because minors are related to determinants also. So they should the number of rows should be equal to number of columns. So there will be minors like 1 by 1, 2 by 2, 3 by 3, etc. Okay, so there will be several minors, but rank will be the order of the minor which is of highest order and it is non-zero. Okay. So it has at least one non-zero minor of order R. Okay. Let me explain this in other way. Say suppose we have a matrix of order 5 by 4, and now from this matrix we are trying to make minors. So one of the minor will be of highest order, which is 4 by 4. Okay, so we will start from the highest one. So suppose we can form 1, 2, 3, and 4 separate 4 by 4 minors. Say we can form. Okay, so in that case, if any of the minor has its determinant value equal to not equal to 0, and the remaining ones are 0, then in that case the rank of matrix will be 4. And suppose all the 4 by 4 minors become 0, then we will shift to the next lower order minor, which will be 3 by 3 minor. And if any of the 3 by 3 minors is non-zero, then rank will be 3. But in the case when all 3 by 3 minors are also 0, then we will further move to 2 by 2 minors. And in this way we we will keep reducing the order, and we will stop where the highest order which is found to be non-zero. Okay. So this statement means that thing. Okay. And also this leads to the condition that every minor of A which is of order higher than R should be zero. Okay. So every minor of A of order higher than R of order higher than R should be zero. Okay. Then R is the rank of the matrix. Now we can using these concepts determine the rank of the matrix. Now returning to the system of equations, we can determine the consistency of the given system of equations. Okay. So suppose we take the matrix M and K from here in the above given case of system of equations in three variables. So we can form an augmented matrix. Okay, so matrix known as augmented matrix is found by joining the matrix M and K. That is the coefficient matrix and the matrix of constant terms. Okay, so again we are talking about the consistency of equations. Okay, so consistency of system of equations. So there may be homogeneous as well as non-homogeneous system of equations. Okay. So let us quickly see them. So if the matrix formed by augmenting the matrix M and K, this is a way to represent the augmented matrix. This matrix is known as augmented matrix. Here I have used the letter A. Any letter can be used, so we'll be keeping this as A. So simply what is done here is the matrix K is added as an extra column in the matrix M. Okay, so suppose we had here A1, A2, A3, we had B1, B2, B3, C1, C2, C3. Now we will add here K1, K2 and K3, and this is the augmented matrix. Here this extra column has been added. I'm drawing these dotted lines just to indicate that this has been augmented here. So like this. Now to check the consistency, we need to find the rank of the coefficient matrix and the rank of this augmented matrix, and based upon that we can predict the consistency. So this is done in the manner that the given system of equations may be either consistent or it may be inconsistent. Okay, so suppose we are now first considering for homogeneous system. Okay. Okay, so let us first consider the non-homogeneous one. Then we will proceed to homogeneous. Non-homogeneous system of linear equations. So there may be any n number of variables here. So it is valid for any number of variables. So suppose we have found the augmented matrix and the coefficient matrix. In our case, it is a 3 variable system. It may be even more number of variables. So suppose we have Ax equal to B is the system. Here we were using some different symbols. So this was in our case mx equal to k is the system of equations, and suppose they represent the rank by capital R. Okay, so what is to be done is simply find the, let us say, rank itself. So rank of this augmented matrix A. Okay. A here represents the augmented matrix. Keep in mind. Let me write it also that this is the augmented matrix. Okay. So find the rank of A and the rank of the coefficient matrix M. Okay. Then here two cases may arise. Okay. That the rank of A may not be equal to rank of this M. Okay. So in that case, rank of A is not equal to rank of M. And in this case, the system is inconsistent and there will be no solution. Okay. So uh, inconsistent, and there will be no solution. No solution. Okay. So this is one case. Now suppose the rank becomes equal. Okay. So the rank of A is equal to rank of M. In this case, again, two cases arise. Suppose we have n number of variables. Okay. So the ranks of A and M may be either equal to the order of highest order minor, means the order of augmented matrix, which will be nothing but number of variables. This will be the highest order possible. Okay. So suppose this rank of A is equal to rank of M, and this is equal to number of variables. Here let us write that n variables. So in this case, what happens is there will be a unique solution. Here the system will be consistent. As soon as the rank becomes equal, the system becomes consistent. After that, it may have unique or infinite solutions. So here it will have a unique solution. Unique solution. And when these ranks are equal but less than n, so when rank of A is same as that of rank of M, let me bring these things to a little left. So suppose the rank of M is equal to rank of A, but it is less than N, then in this case there will be infinite solutions. Infinite solutions. So this is the method to check the consistency of non-homogeneous system of equations. Okay. So now let us see the consistency condition for system of homogeneous equations also. Okay. So homogeneous system of equations basically means that there will be no constant term on the right hand side, only there will be variables and their coefficients, and the right hand side will be zero. Okay. So in case of homogeneous system of equations, system of linear equations, say n variable again, so n variables. So here again, the concept of rank can be used to predict the consistency. So here, say we have the system as mx equal to 0. Right hand side will be a null matrix because the constant terms on the right hand side are all 0. So here again, we need to uh, see this type of equations will always have a solution. The solutions will now be either trivial or non-trivial. Trivial means a unique solution where all the variables are equal to 0, and the other case is there will be an infinite number of solutions or non-trivial solutions. Okay. So this, uh, let me erase first. This type of system always has a solution. So always has a solution. Now to check the consistency, find the rank of A. That is the augmented matrix. Okay. And simply there will be two cases only. Those two will be either trivial or non-trivial. Okay. So if the rank of A is equal to n, then there will be unique solution. Unique or trivial solution. And in this case, so there is unique or trivial solution, and each variable is equal to 0. This will be the solution. And in case the rank of A becomes lower than n, then there will be infinite number of solutions or non-trivial solution. So infinite or non-trivial solution. So these are the methods to check the consistency of system of equations. Okay. So let us stop for now, and in the next class we will see an example to solve a given system of equations, in which we will be implementing the concept of this finding the inverse of a matrix also. Okay. So for now, let's stop here. Thank you.